Alright, so in this video we're going to be talking about the SN1 reaction. So this is, as the name implies, pretty similar to the SN2 reaction. The big difference is, instead of bimolecular, it is called unimolecular. And we'll get into the differences there. But this is the general reaction scheme for a SN1 reaction. And now it might be tempting to look at this and say, oh, can't this just be an SN2 reaction? Right? Can't we just take this lone pair, attack the backside, make the group leave, and then we have the products? Well, it's tempting to do that. The SN1 reaction operates on slightly different rules. And we'll get into sort of the nitty-gritty details of why there's differences there in a little bit, probably in the next video. But essentially, right, for an SN1 reaction, we have to look at the rate law. And so what it means is it is dependent on not the electrophile and the nucleophile, but just the electrophile. So it is a first-order rate law. It's dependent only on the concentration of the electrophile, hence why it's called unimolecular. So what does that mean? What does it mean to just be dependent on the concentration of the electrophile, right? Remembering that this is our electrophile, right, and this is our nucleophile. And so when we're looking at the mechanism, right, we have two steps, typically. For the first step, right, we just have the electrophile here. What happens is the leaving group, right, chlorine, leaves on its own, right, without any intervention from the nucleophile. And we use equilibrium arrows here to show that this process is pretty reversible, right, with a positive charge on that carbocation now and negatively charged chlorine, because it is chlorine itself is a good leaving group too, right, because it's sort of that bigger than fluorine halogen. That negative charge can be sort of localized through the molecule, through the atom, so it is a pretty good leaving group. And so this is the rate limiting step, right? It's dependent on the concentration of the electrophile because this reaction is slow. You can imagine why it's slow, right? Because you have a chlorine leaving without any intervention from the nucleophile. So this happens, right, regardless of how much of the nucleophile there is, because it's not influencing this first step at all. It's only the electrophile that has any influence on what's happening here. And generally, and I'll mention this again in a little bit, tertiary electrophiles, right, because this carbon is bonded to three other carbons, are much better at these SN1 reactions, right? Because remember our rules, right? Tertiary carbocations are much more stable than secondary, primary, or methyl carbocations, right? So this plays a big part, right? The more stable the carbocation is, the quicker this rate limiting step is, the quicker this first step is. And so in the second step here, as you can probably imagine, we actually have the nucleophile reacting with the electrophile. Right, this oxygen here attacking that carbocation center to form that new covalent bond. Right, and typically it just happens in two steps. The only time there might be an additional step is if, for example, if this wasn't O- but OH and it attacked, you'd have a positively charged oxygen with the hydrogen coming off that we'd have to do an acid-base reaction to remove, and we'll look at that in a lecture example problem. But for SN1 reactions, typically just two steps, one where the leaving group leaves, and then the nucleophile attacks the now carbocation intermediate, which we discussed in detail in chapter 4. So looking at the energy diagram for this, it looks a little bit different than SN2 because there are now two steps instead of just one. Right, so we have our reagents and our intermediate, right, with the reagents, of course, being our electrophile and nucleophile, and our intermediate is, right, this carbocation intermediate. And we have our first transition state here, right, similar to before, where we just have the, essentially, the chlorine leaving, right, and partial negatives and positives show the bond is breaking, right? And then we have our next reactive intermediate, and you notice this hump here is a little lower than the first one, right, because this is a rate limiting step, so this is more energy, right, required to get to the intermediate than this next step, which happens a lot quicker, right, or with a lot less energy, right? So that is our second transition state, where, as you can imagine, it is just the, right, just the reactive carbocation reacting with the nucleophile. Right, and again, we show partial negatives and positives to show that there's a bond being, in this case, made. Right, before it was being broken, now here it is being made. So very similar to the SN2 transition state, except for now it's all happening in 2 steps instead of just 1 step, where there's both that bond breakage and being formed at the same time. Right, and we have finally our products here. Right, these final 2 species that made it through the SN1 reaction. Okay, very similar to the SN2, just again, there's 2 transition states because there is an intermediate right from that first step in the SN1 reaction to get to our final products. So now we have to look at the effects of the substituents on the rate of the SN1 reactions. And inversely, the SN2, right, where a smaller carbon center was more reactive, now is the opposite, right, where we have tertiary carbons, as I mentioned, being fast, and then the methyl carbon center being slow, right? Again, that all comes from the carbocation intermediate, right? Because a tertiary carbocation is way more stable than a methyl carbocation, right? Again, it comes from those inductive effects, right? Because those carbons are slightly partially negative, right? Because they're pulling electron density from all those hydrogens, right? Those 3 hydrogens that are on each of these methyl groups, right? It helps to stabilize that carbocation center. And for this carbon, right, there's nothing to help stabilize it, so it's very reactive. And it's the point where, for SN1 reactions, we almost exclusively only see SN1 reactions happening with tertiary and secondary carbocations, right, almost exclusively. Right, and it barely happens at all with primary or methyl carbocations, right? So we're pretty much only going to see SN1 reactions with these, and as I mentioned in the last video, with SN2 reactions, you pretty much only see them with methyl, primary, and sometimes secondary. So there's a little bit of overlap with secondary carbons there with SN1 and SN2 reactions, and we'll learn in a little bit in the next couple of videos how do we tell if it's an SN1 reaction or an SN2 reaction. Furthermore, right, as we've mentioned in chapter 4, we can get an even more stable tertiary carbocation when we have the chance for resonance, right? So if this was an SN1 electrophile, we would be left here with, right, a positive charge on a carbon next to an sp2 carbon, which we know can do resonance. Right? So we can do this for allylic carbons, so carbons next to a double bond, and benzylic carbons, right? Carbons next to a benzene ring or an aromatic group, because they can do resonance with the tertiary carbon intermediate. And so these will be faster than tertiary carbocations. And so now what about the stereochemistry, right? Remember in the SN2 videos, we showed that SN2 reactions had inversion of stereochemistry. Here, that doesn't exist. If we had a carbon, right, for example, with, let's say fluorine, bromine, and chlorine, right? And we had, let's say, iodine as our nucleophile, right? Where would this inversion, or what would be the stereochemical outcome of this? And the answer to that is that there isn't, because, right, if we look at the intermediate here, right, remember that we have, right, because this is a positively charged carbon, we have an unhybridized p orbital, right, because this is an sp2 molecule, right, or an sp2 carbon. So that means when the iodine, right, or any nucleophile comes in to attack, it can either come in from the top or the bottom, because there's no preference here, right? This is a flat molecule, right? It's totally planar, right? Trigonoplanar, of course, because of sp2 geometry. So it'll either come from the top or the bottom, meaning that there is no stereochemical outcome here, right? And if we tried to draw it with any sort of stereochemistry, we would see that we would be unable to do so, right? Because in one case, if we had the iodine attack from the bottom, if we had the iodine attack from the bottom, it would look like this, right? And if it attacked from the top, everything would be pushed down, right? And if you try to do R and S configuration for these molecules, you'd find that they are different, right? They are not the same stereoisomer, right? They're enantiomers now. And so what we call this, right, for SN1 reactions, we have a racemic mixture, right? It's meaning a 50-50 mix of both enantiomers. So in short, we don't need to worry about stereochemistry for SN1 reactions. And we'll go over that in some of the examples we will do in lecture. So in lecture, we're going to go through some different SN1 reactions, including mechanisms, and we'll also go ahead and take a look at the rate of reactions for electrophiles and determining which of these electrophiles has the leaving group leave the fastest.